Welcome to The Explainer. Today, we are diving into one single star system that's acting like a cosmic laboratory, and it's helping scientists solve two totally different puzzles at the exact same time. Let's get into it.
Our story starts with a number, 510. That's how many light years away this thing is, tucked away in the southern constellation of Pictor. Now, in cosmic terms, that's practically in our backyard.
And trust me, this is not a quiet neighbor. What we're talking about here is a binary star system on an absolutely incredible supersonic journey through the galaxy. They're moving so fast, they're literally just plowing through all the gas and dust that fills the space between the stars. So this system, Pulsar J0437-4715, is basically a perfect natural laboratory. By studying the physical wake it leaves behind, and by listening super carefully to the signal it sends out, we're uncovering brand new clues to some of the universe's biggest mysteries.
All right, first up, let's get properly introduced to our main characters. We've got a pulsar, which is a super dense, rapidly spinning dead star, and its much smaller buddy, a white dwarf.
The pulsar is the real heavyweight in this pair, packing about 1.4 times the mass of our own sun into a ball no bigger than a city. Its companion, the white dwarf, is what's left of a much smaller star, and it weighs in at just over a fifth of our sun's mass.
Now, these two are locked in this incredible cosmic dance. Because a pulsar is so much heavier, their shared center of gravity, what we call the barycenter, is super close to the pulsar itself. So what's the result? Well, the pulsar barely even wobbles, while the little white dwarf gets whipped around it in this tight orbit, finishing a full lap every 5.74 days. And this is all happening while the whole system is just blasting through space.
So, what do you think happens when a system like this travels faster than the speed of sound through all that interstellar gas and dust? You get a cosmic spectacle.
It creates something called a bow shock. You know, it's pretty much the same idea as the wake you see from a boat speeding through water, or the sonic boom from a supersonic jet. This pulsar system is literally pushing a wave of interstellar gas ahead of it.
For years, astronomers have seen these bow shocks in certain kinds of light, like that reddish H-alpha light. But just recently, using the incredible power of the Hubble Space Telescope, scientists pointed it at J0437-4715, and they saw something totally new: the first ever detection of a pulsar bow shock in far ultraviolet light.
And what's really amazing is just how different this new view is. These observations showed that the energy pouring out of the bow shock is 10 times brighter in far ultraviolet light than in the H-alpha light we were used to seeing. This tells us the physics of these shocks are way more complex and energetic than we ever thought.
But you see, the physical wake it leaves behind in space, that's only half of this amazing story. The other half is found hidden deep inside the signal the pulsar beams directly to us here on Earth.
You know, pulsars are basically nature's most precise clocks. They spin hundreds of times every single second, sweeping a beam of radio waves across space just like a lighthouse. And from our perspective here on Earth, we see a pulse with almost perfect regularity.
This incredible precision is exactly why astronomers use dozens of them all across the sky to build a galaxy-sized detector called a pulsar timing array. The whole goal is to detect the incredibly faint, subtle stretching and squeezing of space-time itself, what we call gravitational waves, as they wash over our galaxy. But there's a catch. These perfect clocks, well, they aren't quite perfect. If you look really close, each individual pulse actually varies slightly in its shape and its arrival time. This creates a kind of statistical noise, a stutter in the data, that scientists call jitter. For a bright, really important pulsar, like J0437-4715, this jitter is the #1 thing getting in the way of more precise measurements, and new research shows this stutter is way more complicated than we thought. The noise acts differently depending on what radio frequency you're listening at, which means our old models for trying to filter it out just don't cut it anymore. So here's the crucial point. To hear the faint whisper of gravitational waves, we have to perfectly understand and subtract every other source of noise, and that includes this complex, frequency-dependent jitter. A pulsar timing array works by looking for these tiny correlated changes across all the pulsars in the network. A passing gravitational wave would cause pulsars in one part of the sky to seem to speed up a tiny bit, and others to slow down, all in a very specific pattern. But to see that pattern, the data has to be unbelievably clean. And this is exactly why all this focus on one star's little stutter is so important.
By taking apart the noise in our brightest pulsar, scientists can build much better models to clean up the data from the entire array. Basically, fixing the signal from this one star helps us sharpen the picture for the whole cosmic experiment. So we're left with this really fascinating connection. From the visible shockwave plowing through interstellar space to the invisible static inside its radio beam, every single aspect of Pulsar J0437-4715 is giving us crucial data. By meticulously modeling this one-star stutter, we might just be able to finally hear the faint, gravitational wave hum from every pair of supermassive black holes spiraling together across the entire cosmos.